Hello everyone. Today we are discussing about the most powerful fluid dynamics theorem, and based on that we are solving one problem. We will also verify our results with the CFD solver, specifically ANSYS Fluent. So if you are into the fluid mechanics or computational fluid dynamics, this is the video which will be useful for you for understanding the Bernoulli's principle more deeply. So let's start it. So Bernoulli's equation is one of the most fundamental principle in the fluid dynamics, widely used in physics and engineering. This equation provides insight into the behavior of the fluid by establishing a relation between pressure, velocity, and elevation within the flowing fluid. So Bernoulli's equation states that the total mechanical energy of incompressible and non-viscous fluid remains constant along a streamline. That means the sum of the pressure head, velocity head, and elevation head remains unchanged. It can be expressed mathematically as P by rho g plus V square by 2g plus Z, that summation of pressure head, velocity head, and potential head will be constant. So where P is pressure, G stands for gravitational acceleration, Z stands for elevation, that is height from the earth surface, rho is the fluid density, and V is the velocity of the flowing fluid. So acceleration due to gravity 9.81 meter per second square generally we consider. So ultimately Bernoulli's equation tells us the total energy along the streamline is constant. Okay, so the sum of pressure head, velocity head, and elevation head is constant along the streamline that we have seen. So this equation implies that an increase in the speed of the fluid occurs simultaneously with a decrease in a pressure or decrease in a potential energy. For example, a classical example of Bernoulli's principle in action is an aeroplane wing. So as air flow over a curved upper surface of the wing, it moves faster compared to the air moving beneath the wing. So according to the Bernoulli's principle, the faster moving air above the wing creates a lower pressure region, while slower moving air below the wing maintain the high pressure. So this pressure difference generates the lift along the aircraft to rise into the air. So another common example is the venturimeter effect. So when the fluid flows through a narrow section of the pipe, its velocity increases while its pressure decreases, as the principle utilized in devices such as carburetors and medical nebulizers. So Bernoulli's equation is a powerful tool for analyzing the fluid flow, and it's fundamental in various engineering applications including aerodynamics, hydraulics, and medical technologies. Understanding this principle helps engineers design efficient fluid system from aircraft wing to piping network and even medical devices. Let's move further. Now, as I said, this Bernoulli equation, if we apply for the fluid which is flowing through the pipe section may be of uniform cross section area throughout the flow, or it may be having converging section, or it may be having diverging section. But as if we apply the Bernoulli's principle for such type of flow where the fluid is incompressible and the flow is inviscous and also the flow is laminar steady state, in that case if we apply the Bernoulli's principle or all the shapes, the equation will be same. For the inlet condition, you can see in this particular left side, V1 rho g V1 square by 2g plus Z1 will be equals to the outlet condition P2 rho g V2 square 2g plus Z2. So this is the inlet condition for each and every case. This principle is applicable for this shape also, this shape also, this shape also. Now if I say for the horizontal pipe, if I am assuming this is horizontal section, means height from the surface will be same for inlet center and the outlet center. So for the horizontal pipe assumptions, Z1 will be equals to Z2, and if we apply this to this Bernoulli's principle, then we can eliminate this Z1 and Z2 and we will have the simplified Bernoulli's equation P1 by rho g plus V1 square by 2g is equals to P2 by rho g V2 square by 2g when elevation is at same height Z1 is equals to Z2. Then calculate the pressure at the inlet using given velocity. How we can identify the velocity? For that we have the continuity equation with us. So continuity equation for the incompressible flow, we are saying Q1 is equals to A1 V1 is equals to Q2 A2 V2. Flow rate, so volume flow rate discharged will be constant throughout the section. So A1 V1 is equals to A2 V2 is equals to A and V. So Q is a flow rate which will be in meter cube per second. A is the area of the cross section meter square and V is the velocity of the flow. So equation first published by Daniel Bernoulli in 1738, which is all about the energy consumed along the streamline. So first is static pressure. If we will see the various forms of the Bernoulli equation. So at present we are saying in the pressure form. So it is static pressure, first term, dynamic pressure and hydrostatic pressure because of the potential energy is constant. So how to convert this into pressure energy, kinetic energy, potential energy, I will discuss in the next PPT. Okay. So first inlet condition as we seen before, and right side it is indicating the outlet condition. So if we move further, as I said, we are defining the Bernoulli's equation in different way. So first energy form, we are saying by dividing the rho P by rho plus V square by 2 plus Gz is equals to constant. So this is the energy form of Bernoulli's equation. Similarly, if we have the pressure form, so P by 1 by 2 rho V square plus rho Gz, this equation is Bernoulli's, but it is in the pressure form, and whatever the generalized standard equation generally we used for defining the Bernoulli's principle is in terms of head. So this is pressure head P by rho g plus V square by 2g is a velocity head, and that is kinetic head, plus this is potential head, Z is potential head, and that if we apply for inlet and outlet condition, you will observe the same equation what we discussed before. Then streamline, come to the streamline. So streamline is the path followed by a single particle in a steady flow. So it represents the direction in which the fluid moves, ensuring that particles do not cross each other's path. So for defining this streamline, we should have defined laminar flow, as laminar flow itself defining that each layer of the fluid will not cross each other. Every layer will be in the parallel position throughout the movement, throughout the motion of the fluid. So we are defining the streamline along the laminar flow, within the laminar flow. So steady flow means the velocity of the fluid at any given point does not change with the time. While the speed and pressure may vary along the streamline, the overall pattern of the flow remains constant. So Bernoulli's equation is widely used in the fluid mechanics, explaining the phenomena like lift in aeroplane wing, water flow in pipe, even though blood circulation in the human body also. Okay, so again next part is we already said the fluid should be inviscous. Okay, so Bernoulli's equation assumes the fluid has no viscosity. This means it flows without resistance. So streamline is the path followed by the single particle in a steady flow, meaning it shows how the fluid moves over the time. Steady flow refers to the flow that doesn't change with the time, so the velocity of the fluid at any given point remains constant. But we never observe such type of scenario in real life problem. So in the real life fluid flow, a streamline helps visualize the direction and behavior of the flow, especially in the complex system like pipes, airflow around the object. So you can see the streamline of this fluid, and this is the direction of the flow, and it is having the movement from initially and up to the final point. It is following the same path. Okay, so that's why we are saying one of the equation states that static, dynamic and release pressure remains constant along the streamline. So as I said, in viscous flow, which says there is no viscosity, so it does not resist the flow of the fluid. But as we know, in the reality, all fluids have some viscosity, causing energy loss as they move. So this makes Bernoulli's equation as idealization rather than the perfect representation. So for defining this behavior of viscosity, we have modified Bernoulli's principle where we are counting the losses at the end. The next equation applies only to the laminar and steady flow. Steady flow means the velocity at given point doesn't change over the time, while laminar flow is a smooth or orderly. If the flow becomes turbulent, moving in a chaotic pattern, Bernoulli's principles no longer holds. Like if I say turbulence flow, so it doesn't apply to the turbulent flow where the fluid moves in a chaotic pattern. Now third condition, incompressible flow. So Bernoulli's equation assumes that the fluid doesn't change its volume as it moves. So this is usually true for liquids but not for gases, especially when they are moving at high speed. Now come to the analytical calculations. As I said, whatever the equations we have, based on that equations we are formulating one problem, and the analytical solutions which we will be getting through the analytical method, same geometry, same input parameters, same boundary conditions we will apply in the CFD and in the ANSYS fluent, and we will check whatever the results we are getting for the analytical values, parameters values, whether it is achievable with the CFD simulation or not. That will be the task for today's discussion. So for that I am assuming one domain, converging domain, where inlet section is having some parameter A1 which is having area of 4 meter square, and V1 is the velocity 1 meter per second I am assuming at the inlet. I don't know the pressure at this point. Now I have the second outlet condition where I am assuming a velocity I don't know, but I am exposing this outlet to the atmosphere. So gauge pressure at the outlet I am assuming 0. Atmospheric gauge pressure is 0. So P2 is 0 in this case. In our case, the continuity equation. Why we are applying the continuity equations? As we know, if we define the problem for this domain, at present we have two unknown. P1 is unknown for us and V2 is also unknown for us. So if we have two unknowns, at least we should have two equations. So what are the equations we will be having? First is the continuity equation and second will be the Bernoulli's equation. So first we will apply the continuity equations to identify another one parameter, that is V2. We have the continuity equation Q is equals to AV, area into velocity. So Q1 is equals to A1 V1 is equals to Q2 is equals to A2 V2. So if I am putting the value for Q1, that is meter cube per second flow rate, so 4 into 1 cross section area A, 4 into 1 is the velocity at the inlet. I am getting the value for 4 meter cube per second for the discharge from the inlet. Same thing will be available at the outlet, which I indicated with the Q2. Then if I apply the again cross section area into velocity equation in the Q2 form, finally I will get the value of V2, which is 4 by 1, which is 4 meter per second. So V2 is the velocity at the outlet of the section, velocity of the fluid at the outlet. Now once I get the value for V2, I have another equation, Bernoulli's equations, to calculate the value for P1. So for that I will, assuming that it is at same elevation, inlet and outlet will be at same elevation, so Z1 equals to Z2, and if I am rearranging the equations, I can easily change this equation into this simple form, simplified form. Now the conditions which are available for analytical solutions is velocity will be 1 meter per second. This value V1 is known to us, P2 is known to us as P2 is 0, So what is unknown? We are having P1 rho g, V2 2g square and V1 square by 2g. But among these values, we know V1 value, we know 9.81 for G, rho density of the water, which is 1000 kg per meter cube, and V2. V2 just now we calculated for based on the continuity equation, so which is 4 meter per second. So I put all the values in this equation, and finally I am getting the value of P1 is equals to 7500 Pascal. So this is the pressure available at the inlet of the converging section. This is the analytical solution. So this is the solution which I am getting through the analytical method. So I have the two equations, continuity equation and Bernoulli's equations, to calculate the value for V2 and P1. So finally, after doing the analytical calculations, I am getting the value of V2 is equals to 4 meter per second, and P1 I am getting the value for P1 7500 Pascal. Now I will utilize this same geometry, same dimensions, same boundary conditions, same thing I will try to replicate in the CFD fluent, and I will at the end I will try to validate my results, simulation results. So ultimately I will try to find out the velocity at the outlet and pressure at the inlet through the simulation method, numerical method. So go to that. For that method, for the simplicity, I have made the geometry for you. This is a simple thing. I instead of utilizing the 3D section, I am having 2D, and in the 2D also, as I said, the flow is laminar. It is incompressible and it is inviscous. So instead of defining complete this shape, I am having axisymmetry option for reflecting the results within the particular domain. So I have this axis. If I want to go for the axisymmetry option, because the results or the contours or the effect of the flow which I can observe above the axis will be the same for the area below the axis. So that's why instead of going for this complete section, I will go for the half section of this particular converging section. So half section, if I am having, I will go for the half section. Now once we have this section, we should have the dimensions to create the geometry in the space claim or design modeler in the ANSYS fluent, right? So to get the value for this height means in the actually it is radius. So to get the value for the radius, I have the equation A1 equals to pi r square, which is a cross section area at the inlet, and pi r2 square, which is the cross section area at the outlet. So based on that area availability, I can easily get the value of r1, which is 1.1284 meter, and radius of outlet r2 will be 0.5642. So I will create the geometry of this shape in the sketch, and I will create this body from the sketch, and that body will be exported to the meshing. So this is the mesh file I am showing here, and these are the name selections, because once we create the geometry, ANSYS don't know where is the inlet, where is the outlet, where is the wall, where is the axis. So we have to inform to the ANSYS that this is the section is inlet, this is the section is outlet, this section is outlet. To have that idea, to give the information to the ANSYS fluent, we should go for the name selection. So this name selection looks like this way once we give in the ANSYS meshing. So these are the steps shown in the PPT, so that how we can execute the solution. So anyhow, same thing we will be solving in the ANSYS fluent. So just to have a look for this. So this is the scale residuals. These are the contours, pressure contours. This is velocity contour. Then finally, as I said, we have observed we are utilizing the axisymmetry option. So for that, we are utilizing the axis name selection in the machine, and once whatever the physics we are observing here, if we have the mirror option, we can show the actual 2D image for complete converging section. So same thing I have done here. and finally what is the unknown value which we calculated with the analytical data. Same data we are uh, identifying with the help of simulation results. So how to identify that I have shown in this PPT. Then finally I will compare my analytical results with the numerical data. So pressure which is available at the inlet, so analytically we identify the value 7500 Pascal. So but in the numerically we got the value 7550.075 Pascal. It is almost approximately equal to the analytical data. And similarly velocity at the outlet, which analytically we identified 4 meter per second and almost 4.011, almost equal to 4, the value we obtained at the outlet of the section. So with this, in this way we are validating our numerical data with the analytical results. Okay, so this is the validation part we can say, and I have shown the pressure counters and velocity counters. This is the half section of the 2D. This is the full section, converging section. Similarly for the pressure section. So that's it. So now we will move to the next part of simulation. So our results pretty close, which is always good sign. This shows that Bernoulli's equations works really well for simple applications, and CFD solver like ANSYS Fluent can be a great way to validate these types of problems we have seen in the PPT. Now same thing we want to replicate in the actual case. Now come to the ANSYS Fluent. So use this for the geometry creation. Now go to the geometry first. Once I open the geometry, you can see the interface, graphic interface. I will go to the look at face and click on the axis visualization, plane visualizations. I will click on the XY plane, then sketching. In the sketching, initially I will go for the inlet section. So inlet section, to create the inlet section, I will be having the radius R1. This is the sketch I needed, the shape which I have defined, converging section, half section I have drawn. So I am giving the dimensions for the inlet section, which is of the value 1 point radius 1.1284, and the value at the outlet, radius at the outlet, we can see velocity value of the radius at the outlet is, so, and radius of the outlet section is 0.5642. So I will put the value of 5642 in my outlet value. So 0.5642 is the outlet radius. Then I will click on the generate. Now this is the sketch I am having. So I need some body, that some domain I have to define. To convert this sketch into surface, I have this concept surface from the sketch option. Click on the surface from the sketch option. Then before applying, select the sketch which is in the XY plane. Select the sketch, apply. For that instruction is given, surface from the sketch creation, select the base object for this feature. Select the sketch, apply and generate. Now we are ready with the one part, one body. Now you can see one part, one body, surface body is available with us. Now this, at present this domain is solid. I am going to change this solid domain into fluid domain, and again I will click on the generate. Once I generate the body, now it is ready for the meshing. So I will close it. Now this geometry is ready for the meshing. I will go to the mesh part, double click on the mesh, it is opening. So once you open this mesh interface, you can see so many options available on the screen. You can see the outline. In the outline, below the outline, there is a details of the project. Click on the generate. You can see outline options are available. This, go to the generate, and once you generate it, to see the mesh, click on the mesh. It is in progress mesh. Now you can see the mesh. So by default we generated, for the by default case we have the element size something by default considered by the ANSYS. So its value is about 0.13996. I want to change this in mm, so you go to the unit, change to mm. Then now you can see at present the element size is 139.98. I'm going to change this to 10 mm. Now it is refining the mesh. It will take some time. Once you generate the mesh, you can see the fineness. We change this from the coarse mesh to the fine mesh, but still we are observing some unmapped meshes. So for that, unstructured meshes, for that I will go for the face meshing, and once you click on the face meshing, we are trying to change all the unstructured mesh into structured mesh, map mesh. You can see the clear view of map mesh, structured mesh properly. So once you click on the generate button with the help of 10 mm element size, click on the face meshing. Now every time we need to give the input values, boundary conditions. For that ANSYS don't know. So ANSYS don't know where is the inlet, where is the axis, where is the wall. So we have to inform to ANSYS. So for that we have some options for the selection. You can see there is option vertex selection. I can select the point from this, and edge selection I can select the line edge. Then there is a face selection, I can select the face, and finally I have the body selection. So now I am selecting the first option, inlet edge selection. Create the name selection. So for giving the name at the inlet, I am selecting the edge selection option and select the edge, right click on it, and create name selection option is available. Inlet, give the name inlet. Okay, say okay. So this v1 we can define at the inlet with the help of that, and outlet similarly I have to define the outlet for 0 Pascal. So okay, inlet and outlet boundary conditions I have to define. For that I should have the naming of these sections, these edges, inlet and outlet. Outlet is available for us, inlet is available for us. Now I am giving the name to the wall, create wall, name as a wall. Right, now this is axis through along which we want to define the axis symmetry. So I am giving axis name to this line. I can see all the name selection by clicking control select inlet outlet wall axis, and you can visualize all the naming which we have given to the geometry. I want to change the color, bluish color to sky blue to white background, so that you can easily visualize the inputs values graphics. So I am changing from blue to white. Now you can see the background is white, so you can easily visualize the inlet conditions, boundary conditions, name selections. Once you done the meshing, you can click on the update. Now mesh is ready for the setup. Go to the setup, double click on the setup, go for the double precision, start it. This interface will be opening for setup. Say okay. This is the view you are observing. Now I said we are defining the half section of converging section. To have the mirror image of this half section at the end, we should have the axis symmetry. For defining the axis symmetry properly, we have given the name selection option in the meshing, that is axis we have given. So that axis naming will help us to give the mirror image at the end. How it will be available I will explain at the end. So go to the model. Next part is model. There is no multiphase, there is no energy, only viscous. For defining the Bernoulli's equations, we are saying it should be the in viscous flow. Okay, so to define it very well in the simulation also, we are saying the fluid is in viscous. We can define that in viscous flow in the particular viscous model. Now there is no other model available, so I will go to the material. Now in the material there is option fluid. So in the fluid we need water as a main fluid in the particular case. So I will go to the fluid database, and in the fluid database I am having the water liquid as a material, fluid flow material. I will copy it, and you can see it will reflect in the material list of the ANSYS. Okay, now initially by default you can observe that initially the value of the liquid is 998.2 kg per meter cube density. Now I am changing this density to 1000 kg per meter cube. 1000 kg per meter cube. This small change I made here. Now close it. Remaining thing no need to change. Now here in this case we have defined the fluid. We have imported the fluid from that fluid database, but ANSYS don't know whether the fluid domain is liquid or air. By default, if we click on the surface body, which is solution condition surface body, you can observing that air, by default it is air. Now our fluid is liquid water, so I will change from air to water liquid and click on the apply. Close it. Then go to the boundary conditions. What are the boundary conditions we have defined? As we know, inlet velocity is 1 meter per second, and outlet is a pressure gauge outlet, atmospheric gauge pressure. You can see here inlet V1 is 1 meter per second and outlet 0 gauge. So I will give the inlet condition first, which is velocity inlet boundary condition. I am defining 1 meter per second velocity, apply, close. And outlet, it is a gauge pressure 0. You can see P2 is 0 gauge pressure. You can see 0 gauge pressure, 0 Pascal. So I am defining this outlet pressure as a 0. Okay, say apply, close. Go to the numerical method, solution method. Now initialization, sorry. So go to the hybrid initialization, initialize it. After initialization you can go for the calculations. You can see hybrid initialization is done. Run the calculations for the 100 iterations. For 100 iterations, what will be the simulation time? That will be defined based on the converging criteria. This is already set and problem is simple. So once I click on the calculation for the 100 iterations, you can see the scale residuals is converging and it is moving fastly. Now you can observing that we have given this 100 iterations, but simulation runs up to 39 iterations, means 39th iteration is indicating that we achieve the steady state condition for the inlet and outlet values for the velocity V2 and P1 also. So now I want to see the value what we have calculated for P1 and V2 through the analytical method. I want to verify with the help of CFD results. Now go to the surface integral. In the surface integral, go to the facet average, then pressure at the inlet I want to check. Pressure inlet I want to check. Just see the outlet pressure first. As we define the 0 gauge pressure, you can see the 0 Pascal at the outlet. Now go to the I want to go to the pressure again. go to the surface integral, facet, pressure, and outlet I want to check at the inlet I want to check. So compute it. You can see 7550.075 is the pressure at the inlet P1. Okay, and what we calculated with the help of analytical, 7500 approximately. So 7500 is the data we have calculated analytically. So we are almost equal to that analytical results. So now check the velocity value at the outlet. First I will check the inlet velocity, which we have given 1 meter per second. So you can see 1 meter per second. Now outlet value is 4.011987. So this is the outlet value, and through the analytical method we have calculated V2 is equals to 4 meter per second. So almost the value is same. You can see if I am comparing the table for analytical data, if I am comparing the data of analytical results and numerical results, I am observing very close values, very minimal change in the variation for analytical and numerical data. Pressure is 7500 Pascal. In the numerical method we are getting 7550, and for the velocity 4 meter per second, that almost equals to 4.019 something, equals to 0.011987 meter per second. So now I want to see the contours, colorful contours for the pressure and velocity. So for that there is option. You can see the option is available in terms of contours, pressure contours. For the pressure contours, you can see the colorful image at the outlet. There is 0 gauge pressure. This blue color is indicating 0 gauge pressure, and velocity. As we observed, velocity is very less. 1 meter per second is very less at the inlet, blue color indicated with the blue color, and red color is indicating high velocity, which is almost 4 meter per second at the outlet. Now this legend, you can see the legend velocity magnitude available in the left side of the contour. So I want to change from that e to the power 00 e to the power 00 you are observing. I want to show it in the simple digit, not exponential values, only the simple values I want to show. For that I will click on, if I will go for the pressure value display, you can see the colorful contour for the pressure again. Now this is the legend I am having. Legend, I want to change the value of this legend. It is in exponential form. Instead of showing the exponential form, if I want to show in the simple form, float form, I will double click on the static pressure, that legends. You can see in the right side precision to exponential number formats. I will change from exponential to float. You can see the change. It is in the value of Pascal. Now you can change the decimal up to what decimal you want to see the values of legends. You can change that with the help of the precision. If we are providing 0 precision, you can see no decimal point available. I will keep as it is, and I can change the orientation locations at above the counters, below the counters, right side, left side, bottom. Everything we can change for the position of the legend. So we can do the same thing for the velocity counters legend also. Okay, so I am clicking on it, and instead of exponential I am changing these to float. You can see the range of the velocity from 1 to 4.19. Now close it. So now, as I said, I use axisymmetry, half section of the converging section. So to see the mirror image for complete converging section, I have the option in the graphics. Go to the graphics, double click on the graphics, go to the view option, and in the view options, whatever the name selections we have given in the mesh, that is axis, along with that axis it will show the mirror image, right? So I will go for the view. In the view there is a mirror plane option. In that mirror plane I will select axis and then apply. Select the axis, then apply. I can get the mirror image of the simulation what we done for half section of the converging section. So in this way we can utilize the axis symmetry option to save the simulation time, and we can have the same colorful counters for this case also, which you can see observed in the particular case. So that's it from my side. So remaining thing we will discuss in the next class, next video, where I will try to cover up the topic flow through venturimeter or orifice meter or backward facing step simulation. So thank you.